Okay, we're going to talk about pressure. And with that, we're going to talk about the pressure differences. That is really a key to understanding a lot about weather and how it forms what's going to happen in the future. So, first, we kind of got to describe what is pressure. So, what is it? It's air exerts a force on all objects it touches. And its force is just a mass of the number of molecules, we'll say, and their acceleration. Are they accelerating downward? Are they accelerating upward, sideways, whatever? But they all put pressure on you. And as part of that, any gas is made up of different gases. And we know that in the atmosphere we have water vapor, we have carbon dioxide, nitrogen, oxygen, and other. Each one of those gases exerts a pressure. Dalton's law just simply says that each one, you add those pressures up, and you'll get the total pressure for that atmosphere or that. So basically, weight. How much of the weight is it? Well, actually, at sea level, it's about 14.7 pounds per square inch. And that's every square inch on your body has that weight. Oh, yeah, but your body pushes back because it has air inside it. So it's not like you're going to collapse or anything, but you are literally holding up a part of the atmosphere where you are. And that's why structures are holding up as well. And we can measure this in a barometer. Most of you are going to be familiar with inches of mercury. That's because the original barometers were made from mercury. We don't use them anymore. But we also, the inches part is an American English unit. So all you did was suck out all the air in a tube, put that tube down into mercury, and it'll mercury go up in the tube so far. That is the force that weighed down on mercury from the air. So that was your atmospheric pressure. And here you can see the different units. I'm used to working in millibars because it makes the math a whole lot easier. But inches is what most people use in the U.S. Oh yeah, another thing. Unlike, say, if you went into the ocean or into a pool and tried to compress water, you're not going to find it compressed. Well, air is a fluid like water, but it compresses. What does that mean? Well, that means pressure is going to change more rapidly down here in the bottom part of the atmosphere than it will up in the upper part, because the air molecules are being pushed tighter and tighter together down here. And here you can see the horizontal variations in air pressure. Notice they're not a lot. For example, this was over basically 24 hours. Here we are at 10, probably 10, 12 millibars. Goes down to about 1,007 millibars, and all the way back up to, say, 10, 19, 10, 18 millibars. That's 10 millibar pressure difference. If you were to think about that in the vertical, 850 millibars up, we'll say the atmosphere is 1,000 millibars at the surface, 850 millibars up, or 150 millibars in the vertical, is roughly 5,000 feet. So think about how fast you would get 10 millibar change of pressure. Wouldn't take much. Less than a mile, and you have 150 millibars of change in the vertical. So the horizontal pressure is much, much steadier compared to the vertical. So rising air temperature increases the kinetic energy in a molecule. We already said that kinetic temperature is related to kinetic energy. Well, think about it. They're hitting each other. They're going to push each other apart. That's one of the nice things about the air is it pushes apart. So when you heat a part of air, those air molecules tend to move further apart. The density gets less. So you're pushing the air molecules further and further apart. Now, that's one of the things why in warm temperatures, a lot of times, the pressure is going to drop some. Now, in cold air, just the opposite. The molecules are closer together, and the pressure is going to tend to be dropped very quickly in the vertical. If you were to go up in a cold atmosphere. And let's just take a peek at that a minute. So today, for example, here it's very, very warm out in the west, in the Midwest right now. So you would think that that would mean that above that, there would be higher pressures. And if you look at the 500 millibar, there is. Okay, now what about up here in the Northeast? Here's a trough of very deep low pressure. Look at this, 45 degrees, 60 there, but much, much colder than down here to the southwest. And here you have the low pressure. So let's go back to where we were here in this one then. So now that we've shown that, other aspect of this is the more humid the air is, the less dense it is. Water vapor is less dense than most of the other air, that different types of gases that make up the atmosphere. So it's going to be a little less dense than, say, a very dry air mass. So that's why in the summertime, hot, humid air is actually less dense, has less friction than very cold air in the wintertime with high pressure. One of the other things about the atmosphere is winds are always moving along in the atmosphere, pushing the air around. So, and because it is a fluid, just like water, except it's air, say you push at the top of the atmosphere, push the air together, well, that air has got to go somewhere, and it's going to tend to push downward. Hits the ground, it's going to tend to flow out because it can't go into the ground. So you can see if you have converging winds aloft, you wind up having diverging winds at the surface. And the ideal gas law is just another law that allows you, if you know two elements, you can figure out the third. For example, if I know pressure and temperature, I can tell you the density. They're all proportional to each other. So if I know temperature and density, I can tell you pressure. So now, atmosphere. Say you expand air. Think about it when it comes out of your bike tire or out of a tire in a car. Feel how cold the air is when you let it out. That's because it's expanding. It is releasing heat. Now, if you push it together, it's required energy to do that. That's why it gets hotter. It's warming. So when air is being lifted upwards, it's going to cool because it's expanding. When it's being pushed down, it's going to warm because it's being pushed together. And they're very important to understand as far as how that works in the atmosphere as far as temperature and pressure changes. And final part here, if we know that the air is going to cool as it goes up, we can come up with an actual temperature change with height, with lapse rate. And this is 9.8 degrees Celsius per 1,000 meters. So basically 5.5 degrees for every 1,000 feet. So if you climb a mountain in West Virginia or over there in Ohio somewhere, a little hill, and go up 1,000 feet higher than you were, you're going to be 5.5 degrees colder if the air is dry. Key point, air is dry. Remember latent heating from before with temperatures. That's going to impact this lapse rate if there's moisture. So with that, the last thing I was just going to show you quick, and let's see if I can get it up here, would just be a quick upper air sounding. One of the interesting things is there's always motion in the air. We've talked about pressure change as well. It impacts the temperature curve in the air. So it's never truly dry adiabatic. So in this case, for example, it's cooling about 7, maybe 8 degrees per 1,000 meters. Down here near the surface, where it's been heating all day and more mixing, really, really hot, there's a much steeper lapse rate. So that is going to play a role in air parcels and other things you're going to learn about here in the future. So let me know if you have any questions about this.